This is Physics 2212, Lab 3. I'm Christian Medina. Introduction and reasons for our data. The reasons for our experiment are to predict the behavior of circuits containing resistors and capacitors, determine the behavior of resistors and capacitors, use multimeters to measure the value of conventional current and voltage, compare the experimental values to measured values. The current in our 2-resistor circuit was 13.7 milliamps. The calculated values were a little bit higher than the measured values, and the greater the resistance in the RC circuit, the longer the time constant. Depending on what kind of resistor we used, either the 10 ohm or the 20 ohm, our time constant was 10 or 20 seconds. Important equations to note are the node rule, which the current entering a junction will equal the sum of the currents coming out of a junction. So the current coming in is equal to the currents coming out. This is due to the conservation of charge. The loop rule, the difference in the potential for a round trip is 0 in a closed path. This is due to the conservation of energy. And electrical resistance. The resistance is equivalent to Ohm's law. R is equal to V divided by I, or voltage is equal to current times resistance. More important equations to note are the resistances in parallel, where you have your resistance in equivalent resistance is equal to the summation of 1 over Rn of all the resistances. This is because parallel resistors act as a bigger resistor. While in series, the resistors act as a longer resistor, therefore R is equal to the summation of just Rn, not 1 over Rn. Capacitance is also the measure of how much charge can be stored in a capacitor for each unit of potential difference. It is equivalent to the charge on one plate divided by the potential difference, also equivalent to the product of permittivity of free space, the area of the plates divided by the distance between the plates. We have some visual models, which the blue dotted lines indicate the use of a voltmeter to measure the potential between points, and the system is the ammeter or voltmeter, the device measuring the current or voltage, the surroundings of the circuit, including the current and the voltage in circuits. This is all the calculations and videos. Here on the left we have all the calculations, and on the right we have the 2 videos of the 20 ohm resistor being charged, and one is creating a 2-resistor circuit. We construct a circuit using 2 batteries, 2 resistors of 47 ohms and 100 ohms, and 2 ammeters. Our predicted current was 0.02 amps. Our observed current was 13.7 milliamps, and our reversed current was negative 13.7 milliamps. 2 is the open circuit. It's the same process as part 1, but replacing the ammeter with a voltmeter. Our predicted value was 3 volts of potential difference and 0 amps, as it should behave as an open circuit due to the high resistance within the voltmeter. Our experimental values was 2.94 volts and a current of 0, so slightly different. Part 3, we measure the voltages around the circuit. So we close the circuit for part 2, and we measure the voltage shown and the diagram from A to H. We had a 2.94 voltage across the battery, a drop of 0.98 volts across the first resistor, a drop of 1.96 volts across the second resistor. This supports the loop rule. Or we have the ammeter in parallel. You reconstruct the circuit so the ammeter is in parallel with the 100 ohm resistor. The current measured in ammeters increased from 13.1 milliamps to 20 milliamps. The voltages are different due to them being in parallel, so the current splits up. Some of the current goes to the resistor while the rest goes to the path of least resistance. This means that the path of least resistance is the ammeter. They both come back to the same value. And here in the bottom right, you can see the picture. Math. Part 5 of calculating resistances. You calculate the resistance of the resistors, ammeter, and wire based on collected data. Resistance can be calculated with Ohm's law, as discussed before. We had a resistance of 49 ohms calculated for the 47 ohm resistor, 105 ohms for the 100 ohm resistor, and 0 for the ammeter and the wire. Part 6 is the RC circuit, charging and discharging. You first have to construct the RC circuit, 2 1.5 volt batteries, a 1 farad capacitor, 2 light bulbs of 10 ohms and 20 ohms. We measure the time taken for the capacitor to charge and discharge. The brightness of the bulb slowly decreases over time in both situations for both resistors. There was 32.1 seconds of charging and 27.69 seconds of discharging for the 10 ohm, and for the 20 ohm it was 66.28 seconds of charging and 58.4 seconds of discharging. The greater the distance means the longer charging and discharging. For the discussion, the calculated values were greater than the actual values seen in the circuit. Could be due to the precision of the ammeter and how the rounding can cause errors, and also due to the usage of the battery. Possible sources of error: measuring tool precision, rounding during calculation, some timing errors when timing the circuits, and no consideration of the resistance in the ammeters and wires. Here are the what-if questions. If we charge the capacitor with no resistance in the circuit, it would reach a full charge in an instant. This isn't true because the wires themselves have a resistance, and so does the voltmeter and the ammeter, and the capacitor itself has a resistance to charge over time. It took about 2.5 seconds to fully charge because of the resistance of the ammeter and the capacitor, so it differs because there's resistance in other things.